welcome to the course Advanced Reaction Engineering. So, in this course we are discussing about the steady state non isothermal reactor designs. So, already we have discussed in our previous class, and today we will discuss about the optimum feed temperatures. So, optimum feed temperature for a non isothermal reactor. So, when we are operating, so then for let us say any particular reactions we have taken a CSTR reactors, and we are maintaining temperature in the coolant outside of the reactors. So, the feed that we are charging inside of the reactors, that may be any temperatures other than the reaction temperature. The reaction temperature may be let us say for a reactions it is 100 degrees centigrade, and the feed we are entering inside of the reactor through the inlet, that may be higher temperature or lower temperature, that may be close to means let us say it is 25 degrees centigrade we are entering. So, that inside of the reactions or reacting mixtures, conversions, yield, product selectivity. So, due to that changes of feed temperature means 25 to let us say 30 degree, 35 degree centigrade, that way if we change or vary the temperature, so then how the inside of the reactor or conversions will vary, that will affect. So, that we will discuss basically. Okay. So, let us say here one reversible reactions we have taken. So, in reversible reactions, and the reactions is exothermic reaction. So, means if we conduct these reactions in this reactor, so here the reactant, that is the feed, that would be charged from the inlet of the reactors, and inside of the reactors the reactions will take place, that is the exothermic reactions. So, here the feed that we are entering may be different temperatures. So, if the operation is let us say it is adiabatic fixed bed reactor. So, its temperature let us say 350, 500 and 600. So, that way if we vary inlet temperature, that is the feed inlet temperature, that way we can express T naught. So, it may be 350, then the reactions will take place inside of the reactor. If it is 500 Kelvin, then also the reactions will take place, 600 also the reactions may take place. So, if we change this inlet temperature of the feed, so what would affect in the conversions or other way the product yield selectivity, that we will see. Okay, since the reactions is exothermic reactions. So, in exothermic reactions the conversions and temperatures, this type of equations we have discussed, that is the energy balance equation. So, this type of equations we have discussed. Okay. So, and material balance equations also we have discussed in your previous class. So, then for exothermic reactions this is the lines, this is the material balance lines, and this is the energy balance lines. So, the energy balance lines is coming from the energy balance equations, and material balance lines is coming from material balance equations. So, if we plot x against temperature, that curve should be like this, means energy balance lines and material balance lines would be like this. So, now we consider at high feed temperature, this is 600 Kelvin, that is the high feed temperature, 350 is the lower feed temperature, and 500 that is the in between of that 350 and 600 Kelvin. So, first we start with the high feed temperature. So, if reactant mixture, that is we are feeding in the reactor, that may be 600 Kelvin. So, then we have to start here, the energy balance lines would be like this, energy balance lines at 600 Kelvin, that lines will be derived. So, then when reaction feed temperature is very high, then what would happen, the specific reactions constant or the reactions would be very high. So, therefore, rate of reactions would be very high. So, then the reactions reach to the equilibriums very fast. Okay. So, therefore, when the reactions will reach to the equilibrium, so means equilibrium conversions is 0.15 let us say for here, for example we have taken. So, if we draw this dotted line, it would reach to the, this is the equilibrium conversions. So, very low conversions we can get. If we start the reactions let us say 350 Kelvin, so this feed temperature is 350. So, then if we plot x versus temperatures, so then energy balance lines would be start from here, this is the 350 Kelvin. So, energy balance lines will start from this is the energy balance line. So, this lines will start from, this is for at 350 Kelvin, it would start here, and if we take 500 kelvins, then it would start from energy balance lines for this. So, whence T0 is the 350, these lines will get. If T0, that is the feed temperature, is 500 kelvins, we will get this, and when feed temperature is 600 kelvins, we can start from this energy balance line like this. So, accordingly, so it has been observed that, means if you notice it, at when 600 or 350 or 500 Kelvin, the feed inlet temperature, 3 different energy balance lines, means if we increase the feed temperature, the energy balance lines shifted from left to right. Okay. So, accordingly, when 350 was there, so equilibrium conversions was high, and when 500 it was close to 38% equilibrium conversion, and when 600 Kelvin, so then feed temperature, then equilibrium conversion is 0.15. So, high temperature if we start, reactions will be specific reactions rate constant, means will increase very, and that would be the numerical value will be very high, therefore, the reactions will proceed very rapidly, and then reactions will very fast reach to the equilibrium. So, then overall, since the reactions started with the high temperatures and reactions reach to the equilibrium, so then overall conversions will get, so means once the reactions reach to the equilibrium, then overall yield product that will get very low. Okay. So, here when we take very low temperatures, means feed temperature is 350, then reactions reach would be very low. Okay. So, when reactions we have started with 350 Kelvin, so then this for this particular reactions, the reactions rate would be, reaction rate constant is too low or very low. So, then overall rate would be low. Okay. Then the conversions will get, that would be also very low, since the reaction rate constant is low, then rate of the reactions would be very low, therefore, the, and at that case conversions is very low. Okay. And at that case equilibrium conversion is 75%. So, when we have started the reactions at 350 Kelvin, means 350 degree feed temperature was there, then the reactions, the conversions that we get very low conversions, but the equilibrium conversion is very high. Okay. So, therefore, this temperature and these temperatures may not be suitable, since here very first when we started with 600 Kelvin, then reactions reached to the equilibrium very fast, and whence we started with the very low feed temperature, then the conversions is very low, or the reactions conversions and equilibrium conversion, there is very gap is there. So, then that temperature is not also suitable. So, in between some temperature you have to choose where we can, means when feed is entering inside of the reactors. So, it would gradually convert into the product, and up to end of the reactors we will get a optimum conversions, neither the conversions would be very low, or neither it would reach to the equilibrium very fast. Okay. So, then we have to choose some optimum temperature of the feed temperature. So, that may be in this case here's conversions is equilibrium conversion is 0.38, and also when the reactions at this particular temperature, maybe the reaction specific reaction rate constant is not neither very low or neither very high. So, in between or close to equilibrium conversions. So, therefore, we have to choose the temperatures at where we can get higher conversions. Okay. So, here's these lines already we have discussed. So, here's you can see. So, here's actually means when high temperature or feed temperature was 600 Kelvin, the reactions suddenly reach to the equilibrium. This is the equilibrium conversions, X is the equilibrium conversions. So, since we have started with a very high feed temperature, so reactions readily converted into the products, since the reactions rate constant is very high. So, therefore, it readily reach to the equilibrium conversions. So, reactions will means reach the maximum conversion, then this is the along the weight of the catalyst or length of the bed, catalyst bed. This is the exit point of the reactors, and this is the starting point of the reactor. So, when the reaction has started very rapidly to these conversions, and then throughout the reactor it would reach the like that way, it would come out from the reactor systems or exit of the reactor at that conversions. But when we have started with, let us say, low temperature 350 Kelvin, that is the feed inlet temperature. Feed inlet temperature is very low. So, then when we have started from here, so conversion is very low. So, then this is the exit of the reactors, then it would reach here, but the equilibrium conversion should be very high. At this case 75% equilibrium conversions. So, then means here means reactions, due to the reactions, the conversion and equilibrium conversions, there is some gap. This is the gap in between these two. Okay. So, then at the exit of the reactors or far away from the reactors, we will get very low conversion. So, therefore, what would happen? So, most of the reactants without reactings will leave from the reactor. So, therefore, the overall conversions, that would be a very low conversions will get when T0 equals to 350 Kelvin. Okay. And when therefore, and when feed temperature is 500 Kelvin, that is at that temperatures we have started here. So, reactions was very low conversions. So, then it would reach to this, and then it would reach to the equilibrium conversion. This is the equilibrium conversions, here it is reached, and then at the steady means same conversions it would reach and leave from the reactors. This is the exit of the reactors. So, that way here the let us say 38% conversions will get. So, equilibrium conversion is 38% at this particular, when feed temperature is this, then equilibrium conversion is let us say 38%. So, there for the conversions may be for this particular, so when x equals to 500 kelvins, then the conversions equals to maybe 35% and equilibrium conversion, that is 38%. This is close to equilibrium conversions. So, and here let us see equilibrium at 350.05 conversions, and equilibrium conversions is very high, 75%. So, here is the basic, this is close to equilibrium value. Therefore, we will choose the temperatures of that feed inlet temperature such a way that we can get or close to reach the equilibrium conversions, but the equilibrium conversion should be means the conversion should be close to equilibrium, but the conversion should be as high as possible as compared to the other conversions. Okay. So, in 600 kelvins when that was 0.15 at 600 kelvin, and equilibrium conversions, that was close to that value, let us say 0.15 that we are getting, so or like this. So, therefore, when conversions and this if we plot, so at 350 conversions is very low, and when 500 Kelvin was, that conversions is very high, and then again if we increase the feed inlet temperatures, so then conversions will drop. Okay. This would be higher than this, but not significantly high. So, then this temperature may be optimum temperature or the feed inlet temperature at which we can get highest conversions or maximum conversions. Okay. So, that way we have to select the optimum feed inlet temperature, that is very crucial or important. Okay. So, now CSTR with the heat effect, we will discuss CSTR with the heat effect for the non isothermal CSTR reactor design. So, this is the conventional CSTR reactor. So, here this is the reactor. So, in the outlet, this is the reactant in, this is product out, this is the conversion and temperature that would be inside of the reactors, and here is the coolant that is passing through these lines at a particular mass rate, and coolant inlet temperature this, coolant outlet temperature is this, coolant that way it is maintaining the isothermal temperature of the reactor. So, if exothermic reactions is there, then the temperature T, that is the inside of the reactor temperature, that always greater than this. So, here means this is the outlet temperature, that would be greater than this is this temperature. Feed the coolant inlet temperature is low, coolant outlet temperature will be high, and the reaction temperature would be higher than that both. And when the reaction is endothermic reactions, at this case the inside of the reactor, that temperature would be lower than the heat transfer fluid temperature, heat would be supplied. So, this temperature would be high, feed the coolant inlet temperature would be higher, and then heat would be supplied to the reacting medium since the reaction has dropped. Therefore, energy or heat would be supplied to the heat transfer medium or fluid, reactant medium or fluid. Therefore, the temperature this would be lower than this. Okay. This is the criteria, and here M is the MC is the mass rate of heat transfer fluid, and TA is the inlet temperature, TA2 is the outlet temperature of the heat transfer fluid. So, heat rate of heat transfer usually we can write this way, overall heat transfer coefficient, heat transfer area and LMTD. So, this way you usually express rate of heat transfer, the amount of heat supplied by the coolant. Okay. So, this way you can write. Okay. So, now the energy balance. Okay. So, the energy balance equations for the on the heat exchanger. So, that we can write this. This is the rate of energy in by flow, and this is the energy out by the flow, and this is the rate of heat transfer through the heat exchanger to the reactor, the amount of heat supplied to the reacting medium or reactors. So, that way we can write here TR is the reference temperature, CPC is the heat capacity of that coolant. Okay. So, this if we simplify it, the equations 1 we can write this way. Okay. So, these two in the left hand side and this is the right hand side, this way you can write. So, Q equals to, if you know the mass rate, heat capacity and coolant inlet outlet temperature, then rate of heat transfer to these systems we can know, and if you know overall heat transfer coefficient, heat transfer area and LMTD, that way also we can write the rate of heat transfer to these systems. Okay. So, now these equations the exit temperature here, see here in these equations, this is the exit temperature, this is inlet temperature of the coolant. So, if we express Ta2, this is the exit temperature of the coolant, this way we can write. Okay. So, here this part we taking. Okay. So, here this equation 3. So, here Q equals to mCp T1 minus Ta2, this we have written. So, now from these two. Okay. So, here equation 3 we can write in terms of left hand side T2, that is the exit temperature, and this exit temperature we can substitute in here in equation 3 Ta2, that is the exit temperature of the coolant that is coming out. Okay. And Ta1, that is the inlet temperature of the coolant. So, then this Ta2 we are substituting in equation 4. Okay, the same equations. So, then the equation should becomes this equation 5. So, just Ta2 we are eliminating, Ta1 that is the inlet temperature and T is the reactor temperature, that way we can expressions. Okay, and mass rate and heat capacity remain there. So, now this component part we are this component part, this we are expanding with respect to the Taylor series, T e to the power minus x we can write 1 minus x plus other components. So, second order terms are neglected, then these equations, this component exponential part we can write this way. Okay, this part, this is the exponential part by considering Taylor series of expansions we can write this way. So, then equations 5 we can write this. Okay, or else we can write Q equals to this. After if you simplify these equations, then it would become this. Here most of the this AMC, CPC, this part would be eliminated and only it would left Q equals to U A Ta minus T, Ta1 equals to Ta2 equals to Ta, or here we are assuming. So, then Ta is the temperature, that is the inlet temperature of the coolant. Okay. So, if we coolant temperature if we know, and then the reacting medium temperature if you know, then rate of heat transfers usually this way we can write. Okay. For CSTR when heat transfer is there or heat exchanger is there, so that way you can write. Okay. So, now Q equals to U A Ta minus T, Ta is the coolant temperature inlet and T is the reacting medium temperature, that way rate of heat transfer we can write. Okay. So, this is the energy balance equations, that general energy balance equation from the beginning of the non isothermal reactor designs we have started and we have expressed this way. So, now if we and in this case we have neglected few terms, that is the considering heat capacity changes between reactant and product components is 0 and shaft work is 0, and then if we substitute this Q in here, this part we are eliminating basically and this part we are eliminating. So, then if we do not eliminate Cp delta Cp, then we have to put it here and only shaft work, that is the Ws equals to 0, that we can put. So, then this equation energy balance equations after putting Q equals to UA Ta minus T. So, we can write the equations is this or this way we can write. Okay. Rearranging these equations we can write in the left hand side we are expressing the conversions part in the right hand side, the temperature components. So, temperature component is right hand side and left hand side is the conversions. So, this is the energy balance equations for a CSTR reactors when heat exchange is there or heat effect is there. Okay. So, then this component basically for heat transfer fluid component UA T minus TA, that is the heat transfer from the heat exchanger or heat transfer fluid. And then if heat of reactions is known, Cp heat capacity of the component is known, feed inlet temperature is known, and molar flow rate of the component, that is reactant entering overall heat transfer coefficient, heat transfer area is known. So, then conversions we can find out if T is known, means at a particular temperature, let us say reactions is 120 degree centigrade is happening, then at that temperature what would be the conversions. Using these equations we can find out. If conversions is given, temperature, what would be the temperature during that time, so that we can find out using that equations. Okay. So, now these equations we have, this is the energy balance equation after substituting this. Okay. So, this is equation number A. So, this is also energy balance equations when Q we are substituting, Ws equals to 0 we are assuming. Okay. So, then these equations we are simplifying this way. Okay. So, here kappa we are taking another some constant terms, Tc another some parameters, not constant, kappa is constant parameters, and Tc is also the temperature parameters. So, for this system, and here we are considering this is I equals to 1 to n, theta is Cp equals to Cp 0. Okay. So, in the energy these equations A, here UA Ta minus T Fa naught, this part we are considering Cp 0, and then the equations we can write this way. Okay. So, means equation A what we have taken, there's this we are assuming, and then we are rearranging that. Here's kappa equals to UA by Fa naught Cp 0, UA Fa naught Cp 0 also here in the bottom denominator will come. So, then this part is basically and this part is basically kappa. Okay. So, here's let this equals to this and Tc equals to this. Okay. So, now this is the energy balance equations, that energy balance equations we are simplifying. Okay. Means in simplest way we are expressing the energy balance equation with CSTR with heat exchange. Okay. So, then equations 8 would come. So, in the 8 equations 8 what we have written in the left hand side minus x heat of reactions Cp 0 1 plus kappa T minus Tc. So, Tc is the one parameters that is shown here, and kappa is another parameters, kappa and Tc, means basically the equation this A was there, we are expressing in terms of kappa and Tc. What is kappa and Tc? Kappa and Tc, that is also all the known components, means overall heat transfer coefficient, heat transfer area, molar flow rate, heat capacity is there. Here also feed inlet temperature, this is the inlet temperature of the coolant. So, that way Tc we are expressing, and kappa is there, kappa is known. So, these components. Okay. So, means basically energy balance equations we are expressing in terms of kappa and Tc. So, then energy balance equations should become, this is the simplest way. Okay. We have expressing, or else these equations we can write this way, or equation 9 also in the left hand side we are putting x, right hand side Cp 0 into 1 plus kappa into T minus Tc by minus delta heat of reactions. Okay. So, equation 8 and 9 both are same, but different way we are expressing. Okay. And equation A and equation 9 both are also same. Okay. Equation A, equation this or this, both all are same equations, but we are expressing or representing different way by considering these other terms. Okay. So, or these equations also we can express this way also, means this rearranging, means equation 9 and 10 that are also same. So, equation 9 and 10 both are same. Here left hand side we are expressing conversions and right hand side putting temperatures. Here left hand side temperature means reacting fluid temperature, and right hand side conversions means conversions. This is temperature versus conversions, and this is x versus temperatures. So, both are same. Okay. So, here the expression is different way we are expressing this equation. So, this is the non isothermal CSTR design equations. Okay. So, this either 9 equations or equation 10, if kappa value is known, Tc value is known. So, this Tc and this kappa value is known. Tc and kappa, what is this? This some parameters. Okay. So, means simplest way we are just all components we are expressing in this way. So, if we know this Tc value and kappa value, heat capacity of the component, heat of reactions, then at that part specified conversions, what would be the temperature inside of the reacting medium under particular heat exchange operation is also there. So, then that reacting fluid temperature we can find out. If temperature is given, then what would be that conversions, means at a particular means reactions is operating here, A is going to be. So, if we measure the temperature reacting fluid medium temperature on that times, what would be the conversions, that easily we can predict using equation 9 or 10, any equations we can use. So, now energy balance equations we know. So, now one numerical problems we will discuss, means how to find out the volume of the reactors if conversions is given. Let us say 60%, 50% conversions if you want to get for a specified reactions. So, then what would be the reactor volume that is required under these conditions. So, that will basically discuss. So, let us say A is going to be one reactions we have taken, that reactions we are conducting in a CSTR reactors with heat exchange. So, for this particular reactions, these are the components should be given. Okay. These are some components should be given or known, means molar feed rate, concentration of the reactant, K0, activation energy, CPA, heat of reactions. These are the components should be known. Once we know, then the volumes we can find out, and before that what we have to do, this is a CSTR reactor, this is the design equations for a CSTR reactor, and this is the red equations, this is the concentration as a function of conversions, this we can substitute here, this we can substitute here, and this K is the reactions rate constant, this is the reaction rate constant at particular temperatures. So, this is the temperature, means reactor temperature, let us say 100 degrees centigrade, this is the T equals to 100. So, at that particular temperature reaction rate constant we know. So, then we can put it here, and then at particular temperature what would be the means conversion if it is given, then volumes we can find out. So, here this is the design equation, let us say one by one. So, these red equations we are substituting here, and rate constants we can substitute here. So, it is a function of temperatures. Okay. So, now molar flow rate conversions, C naught if we know, and KT value if we are able to find out using this all these known parameters here, except this other parameters should be known. This T1 value and K1 value at this particular temperature, K1 value should be given. So, this I said, and activation energy and R that should be known. So, then the volumes we can find out using all components we have to put. Okay. So, now the energy balance equations we have discussed here, means just we have discuss the energy balance equation is this way you can express. This is the these equations or this equation, this is the energy balance equations for CSTRs with heat effect, just we have discussed. So, these equations we can rearrange on this way, equation 9 or equation 10 we can write this way. So, here's kappa equals to this and Tc equals to this. So, then this kappa and Tc value we have to find out by putting feed inlet temperatures, heat exchanger fluid inlet temperatures, overall heat transfer coefficient, heat transfer area, Fa naught, Cp know, then kappa and Tc value we know. Then kappa and Tc value we can put it here, and Cp naught is known, heat of reactions for this reactions is known. So, at specified conversions I said, so if a conversion is given, that is let us say 60% conversion. So, that first we have to know the temperatures. If we put x equals to let us say 60, then corresponding temperatures in the reactor temperature you know. Once we know these temperatures we can put it here, this temperatures we can put it here, then KT value will come out, then KT value we can put it here, then volume of the reactors we can find out. Okay. So, this is the way, means step by step. So, using energy balance equations and mole balance equations or design equation of the CSTR, means CSTR design equations or material balance equations you have to use. This is the design equation, here K value you have to put, and K value to get the K value we need to know the temperatures. So, the temperature once we want to know, then what we have to do, we have to this energy balance equations we have to express this way, and there's kappa and Tc value we have to find out by putting all known parameters. Those things we have to put it here, heat of reaction Cp0 if you know, then temperature we know, this temperature we can put it here, then Kt value will come out, Kt value we have to put it here. Okay, then Fa naught Xa is known, Ca naught is known, and then volume of the reactors we can find out. Similarly, means another example 2 also, reactor volume is specified, that is 10 dmq, let us say it is given. So, conversions versus temperatures we have to find out a plot, means what would be the conversions and what would be the temperature in that case. Similarly, as we discussed, so let us say reaction, these reactions we are going to conduct inside of the CSTR reactor. This is the design equations, and this is means this design equations we can write. This is the rate constant for this particular reactions. The rate constants we can write or expand this way, and this rate we can put it here, this K we can put it here, this Ca we can put it here. Similarly, as we did earlier, so then these equations would become this, or here volume is given I said. So, V by V naught that is equals to tau, that is the space time V by V naught. So, or we can write this. So, here V into Ca naught by Fa naught. So, here V is there, Ca naught means here this equation. So, whatever we get here this Ca naught if you cancel out. So, then V naught is there and this V is there. If we simplify this equation, so you will get V by V naught equals to x by k into 1 minus x, this way it is coming, okay, and V by V naught equals to tau. So, then after rearranging, so we can get this. This is the material balance equation for the irreversible reactions, for these reactions if we conduct. So, then this is the energy balance equation, and in the energy balance equations k equals to this we know as a function of temperature. So, then in k here and here in the denominator both the places this we are substituting. Okay. So, these equations we can write this. So, this is the material balance lines and this is the energy balance lines. Okay. So, from the design equations we have developed this, and from the energy balance equations already we know these equations already know. So, therefore, I am not writing here. So, these equations and these equations we know. So, now both the equation 1 and equation 2 we know. So, this is called material balance equation, this is called energy balance equations, this is material balance equation. So, now here's right hand side whatever the component are there except T, other components should be known. So, then if we plot x versus temperature for material balance equations, so then these lines would be come, this S type of curves would come, okay, and from energy balance lines except T, other components should be known, okay. So, then if we plot Xc versus T in the same graph, so then these lines would come, this is called energy balance lines, okay. So, then energy balance lines and material balance lines we are plotting in the same graph, they are crossing at this particular point. So, this is the steady state temperature you can say. So, at these temperatures we have to operate to get the optimum conversions, or that is the equilibrium conversion, and this is the equilibrium temperature, maximum conversion temperature is this, okay. So, this way we can find out, calculate the conversion and temperature if volume is given. So, we can find out equilibrium conversion and that particular temperature is required for that particular reactions, okay. So, this way we can solve, or either way we can use Polymath software, that is the ordinary differential equation and that is nonlinear equation. This is the, these are nonlinear equation, not differential equation, these are the nonlinear equations, okay. So, Polymath software is there, nonlinear equations 1 and 2 we can solve this material balance and energy balance equations if all parameters are known. These are the parameter that is called explicit equations or parameters that is like tau, A, activation energy, R, here U, A, Fa naught, Ta, theta I, Cpi, heat of reactions, delta Cp, Tr, reference temperature. These are the explicit means components should be known. So, here here in the green shade, so here all these known parameter components we know, means for this particular reactions we should know. So, these are the components, and these two equation nonlinear equations you have to put inside of the polymath software. So, polymath software is there that you have to open, and for the nonlinear equations we want to solve, these are the two nonlinear equations. So, once we solve using these parameters, these two equations, the corresponding means initial value sum should be theirs, means conversion and temperature, and then once this equation nonlinear equations 1 and nonlinear equation 2 that we have put with this explicit equation, this is the results by polymaths. Okay, the results will come. So, this is the conversions and temperature, this is conversion 0.363, and at this particular temperature reaction rate constant value also will come. So, means here's these particular points each 0.366 and corresponding temperature is 563. So, that using means these are the explicit equations or component value we have to supply with these nonlinear equations. So, using polymath software also directly we can find out, or we can get this curve, or else individual points we have to point, and then x versus temperatures for material balance, x versus T for energy balance, both the lines you have to draw, and then you have to plot. Means numerically, graphically we can put it, means get this curve, or using polymath software also similar, means tables will get x versus T table 1, x versus T table 2, this would get, and then we will plot x versus temperature, then this type of curve will comes, and another this will comes if we plot both. So, this way we can get, means from even in this software also, if we want to get, means that in the form of table, that tables also would gives, if you want to get in the terms of plots, that also would give. Okay. So, this way we can solve. Okay. So, thank you. So, today is up to this.